Thank you. So yeah, I actually forgot to make the title the same as in the abstract. So yeah, it's copulas in Stan, but also maybe truly it should be a very specific type of copulas in Stan, and more generally maybe how you can think about copulas and model them. But yeah, I'm Brynjolfur Gauti Guorunar Johnsson from University of Iceland. So yeah, we have discovered Stan in Iceland. But I'm going to first start with maybe a kind of a simple example. So here you see I've generated a normal, you could call it a normal time series with mean 0 and some sort of AR1 process based on a precision matrix. And yeah, that's fine. But maybe we see data that looks like this. It's hard to say if this is a normal time series or whatever this is. But maybe I tell you that I made the data by taking this normal time series, changing it into a uniform variate, and then doing the generalized extreme value quantile function. So I basically took this dependence structure from the normal data and kind of changed it into an extreme value time series with that same kind of dependence. And if we plot it all along here, you can, so kind of the data generating process goes from making Gaussian data and then applying the probability transform to make it uniform, and then a quantile function to make it into extreme values. That's kind of a general workflow in the data generating process, but then of course when we model it, we might go back in reverse. And if I were to generate, say, a time series with negative correlation, then you can see that if this Gaussian variable is above 0, next time it's likely to be below 0. And that kind of translates to, in the uniform variable, if it's above the median, then it's the next time going to be below the median likely. And that will also translate to these generalized extreme value time series data. So what's going on? We can say that all of our YTs are marginally generalized extreme value data. But then the whole vector has dependence that's modeled by some kind of copula. In this case, it's a Gaussian AR1 copula. And the way to estimate all of this is you have these sort of different densities, and then you can work with that. And in the copula sort of a branch, you always have this main theorem, branches of statistics and math. So Sklar's theorem says that basically for any multivariate distribution function, you can write that up as lots of marginal functions and then some sort of dependence function. So I'm a PhD student and many of you are. And so we spend a lot of our time, our job is being confused pretty much, yeah? So I was confused for 2 years, but then I realized, oh yeah, it's just the density. This, you differentiate it, you get this, you take the log, and then it's a log density. And we know how to work with densities. So from Schwarzenegger, if it has a density, we can estimate it. So no fears. So this is sort of an intro to the introduction. So now, the way we would perhaps do this in Stan, so we have just the normal Stan model, where we have some data, and then we have some sort of log probability density function for the marginals. Then we go over the data and make them uniform. Then we can pass that into some sort of copula log density function. And adding that all together, we can sample from that and get some estimates. So in my case, I'm working with extreme rainfall data. So the UK is climate projections. So they give sort of projections far away into the future. We have it's UK gridded into 5 kilometer squares, and we have 44,000 locations. And in my case, I have a generalized extreme value distribution with a trend. So we have 4 parameters per location. All of them are spatially dependent. But then we have this sort of spatial dependence, which we do with iCard stuff. But then we also have this data level dependence that might be left over. So the things I needed to do is find ways to calculate this while I'm still in my PhD. So a little bit of a refresher, if you're calculating Gaussian densities, there's basically two things you need to worry about. It's a log determinant and a quadratic form. So a little bit of a review of all the spatial models. If you have a conditional autoregressive model, you have some sort of dependence parameter governed by alpha. Now, the bad thing about doing something like this in a sampler is that maybe you propose an alpha, and then you have to create the matrix, calculate the determinant, and then do the quadratic form. So the intrinsic or ICAR models, you just have the same Q, and then you just multiply that by some precision, so you never have to calculate the determinant because it's fixed. And then you get this BIM and BIM2 models, which kind of add a non-spatial error back so that you can kind of have your cake and eat it too by having some sort of both spatial and non-spatial like in the car models, but you still don't have to calculate that large determinant. So in my case, we can fit this BIM2 model to these parameters in distribution, and that's fine. That's kind of a solved problem. If you open the slides, on my website, bggj.is/stancon24, you'll see there's some citations, and there's a great paper by Mitzi Morris and others where they are implementing the BIM2 model in Stan. So doing this sort of spatial modeling of parameters, it's kind of solved. It takes some time, but we can do it. But what kind of happens in my case, so let's say I fitted these models, and then I do posterior predictions, and So I take these parameters and I estimate the marginal functions, and then I do what I said. I take the data, I transform it to a uniform variable, and then I transform that to a normal variable. And then we look at, is there any sort of leftover dependence in the data? And here we're seeing that kind of, so I like to say that statistics is about being wrong, but not systematically. We're always wrong randomly. But here we see that we're kind of wrong systematically because there's a sort of a partial correlation between your neighbors and how wrong you are in your prediction, which would say that we need some kind of copula. So what I'm working on doing, and we are working on doing, is that so we have these marginal CDFs, we can model their dependence, but then we need some sort of copula. And a Gaussian copula is nice because we can use a precision matrix. But the hard thing is that when making these precision matrices, their inverse is not necessarily a correlation matrix, because remember, we're sort of taking a uniform variable and doing the Gaussian quantile, so it needs to have variance 1 everywhere. So a little bit of cool linear algebra. So we define our spatial precision matrix Q like this. So we have these one-dimensional AR1 matrices, and we plus them together with a Kronecker or a tensor sum, and then our final matrix looks like this. So this is sort of a block matrix. And you can think of it sort of like each block models some sort of horizontal or vertical dependence, and then the rest is the other dependence. And what's cool about defining it like this is that because of how the matrix is defined, we know all of the eigenvectors and values of big Q just by knowing eigenvectors and values of little q. So maybe the little q's can be 200 times 200 matrices, so big Q would be 40,000. But we only have to do sort of eigendecompositions of the smaller matrices, which is awesome. So we can use some pretty elementary linear algebra to find out ways to calculate these marginal standard deviations by this sort of crude Q matrix, just by looping over these eigenvalues and vectors of the smaller matrices. And what we do then, we gather them in this vector of marginal standard deviations. And I've done some writing up in C++ with RCPP to make it fast. And a very naive case study, if we have like a 50 times 50 matrices, and for example, let's say we want to calculate this by just solving Q, that takes 1.16 seconds. INLA has a function INLA QInf that uses algorithms that Rua has written about using the Koleski decomposition. So that function is not very efficient because it writes out the matrix and reads it again, but so that's 400 milliseconds. But looping over these eigenvalues, it took 1.3. So there's something there. It's pretty quick and nice. But how do we get from there to calculating a density? So if we don't scale anything, if we just use this naive Q matrix, we can all just loop over these eigenvectors and values of the smaller matrices, and we can calculate the determinant by just looping over the eigenvalues. Very nice. And the quadratic form, we can kind of make one eigenvector at a time and then just loop over all of the eigenvectors, so that can be very parallelized and just accumulate all of the quadratic sums, which is nice. But to make it scaled, we have these marginal standard deviations, and inside each loop, before we are doing these computations, we create eigenvectors and values, and then we scale them, and these scaled vectors and values, tilde, they will then be the eigenvectors and values of this scaled Q matrix. Nice. So I'm going to go into it very quickly, but in August I also found out about this pretty cool approximation called a folded circulant approximation. Basically, you double your data. If you have 1D data, you mirror it. We can go over it later sometime if you want to talk about it. But the thing is, you get to do fast Fourier transform computations, and still you don't have these circular boundary effects, which is very nice. So we could just write out this exact model, as I'm doing at the moment, in Stan, and then you should be using the tuple thing, which is very nice. And so we can just loop over this and write out this to calculate this density. And then I also realized, so I wanted to do some sort of Lu CV stuff, but I'm calculating this density for a whole matrix at a time, the whole vector at a time. But then just on Monday before coming to the workshops, I was reading some recommended material from Aki, and so they have these ways to, you know the marginal distributions of all the variables if you have the precision matrix. So yeah, I guess, good to come to StanCon and find out some new things. And this is the code for calculating this approximation. And again, if you want to look into it better, you can follow the link if you want and go over that or talk to me. So I'm working on this package where we can sample data from sort of these standardized copulas. So here I'm sampling a very large spatial field, and I'm trying to plot out the variances and the means. And of course, they won't be exactly 1 or 0 because of sampling distributions, but yeah. But they have the correct sampling distributions. And an example of just using maximum likelihood to calculate these things, you can just write out sort of the marginal log likelihood and then the copula log likelihood, and then you can optimize that. This is also a naive example, but a way to show how, it can be simple. I've done some benchmarking on the code to see a Koleski composition is the classic way. You hear a normal distribution, you think Koleski, right? I was surprised to see that it was also faster in the unscaled case, so 75% faster. And if we're doing the scaled, so that it can't be a copula, we're just adding around 30% time. So I'm thinking that this could be something I could actually start to do in a sampler. So yeah, the key things I've been doing is sort of working on this algorithm to compute densities, basically for spatial normal distributions with marginal variance 1. And this folded circulant approximation makes it even faster. I got into a place where I could probably do this copula modeling inside the same sampler as the sort of marginal modeling, which helps us with keeping all of the uncertainty together, because very often the workflow is to estimate the marginals because they can be quite unbiased even though you don't have the copula, and then you estimate the copula afterwards. But yeah, my future work on this is I'm going to expand this to T copulas, other environmental data sets, and finish sort of my work on this package and my drafting paper. And yeah, I'd like to thank my advisory committee. Birgir Hrafnkelsson is my advisor, and Rafael Huser and Stefan Sigurd are also on my committee.
Time for questions? Please?
Yes, sorry if it's too basic a question, but we should try to incorporate dependence through hierarchical specification, prior specification, instead of using Copulas.
Yeah, so we're modeling the parameters hierarchically. So kind of this distribution has 4 parameters. And we're saying that we're modeling each parameter spatially, hierarchically, so they're drawn from some spatial hierarchical distribution. But the thing is that when you exit, the comfortable couch of the normal distribution, that sort of hierarchical dependence, it doesn't go over into the data level, because you just have lots of these sort of marginal distributions that you're fitting together.
I have from your results, it looked like the scaling was really good, but like the quite a few numbers. So my general question is, how does it scale, like in terms of O, when you scale up the amount of data points in each dimension?
Do you mean like replicates at each place, or just the size of the grid?
Let's start with the size.
Yeah, so when I had, for example, my size, which is around 220 times 220, I could do this sort of scaled exact computations in just under 1 second. But then this sort of folded circulant approximation, it takes 13 milliseconds because of the power of the FFT. So I'm really looking into using that for all of these large-scale computations. But for small data, like very small, in Stan, for example, using an exact, the exact method can be faster because the FFT can have sort of a high, like baseline computations, but then that scales very well.